StatQuest is growing up. StatQuest is growing down. StatQuest is growing. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to be talking about decision trees. Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes-no data. Notice that the cutoff for resting heart rate isn't always the same. In this case, it's 100 BPM on the left side and 120 BPM on the right side. And the order of questions on the left side, first about resting heart rate, then about eating donuts, nodes. We are ready to. The first thing we 6-4.
In this video, we'll start to look at decision trees. Decision trees. And we'll focus on the CART approach to decision trees as introduced by Bryman et al. And it turns out, so decision trees are an extraordinarily conceptually simple approach to classification and regression. But it turns out that despite their simplicity, decision trees can be extremely powerful, especially when coupled with some randomization techniques that we'll talk about a little later on. They can give essentially the best performance of any current algorithms. Very surprising. So remember the basic setup, as always in supervised learning, is we have some data, and we're given a new point x or a bunch of new points, and we have to associate a y with the new x or x's. So the main idea behind decision trees, at least in this formulation, the CART formulation, is you form a binary tree and you minimize the error in each leaf of the tree. So that's the main idea. I will explain what that means through an example. So let's say these x's are in R2, something nice and simple that we can draw. So we've got our nice R2 here, and let's draw some points. Let's say maybe we've got some ones here, some red ones, and maybe we've got some ones down here, something like this, and maybe some ones here, something like that. And then we've also got, of course, another class. Maybe this one's got some zeros, some points which are labeled 0, something like this. Maybe something like that. Now, we have our data set. These are all points, and each of them has a label. And in a decision tree, you choose a sequence of binary splits of the data. So first, let's say, if you want to split this data in some good way, maybe a first choice would be, let's split on the first coordinate here. So let's split on this coordinate. That would be a good choice because we can separate all these ones over here from everything else. And then maybe for the next split, so now we have two regions. So this divides R2 into two disjoint regions. And now we consider each of these regions. This one looks excellent. Everything's the same. But over here we need to do some more splitting, perhaps. So let's choose this one, say. Maybe we choose split. Now we separate this into two regions again, and maybe we're going to split something like this. And then maybe we'll split here or something. Maybe we'll split that one also. So this gives us some nice separate regions, and this defines a tree, a binary tree. So what's the binary tree associated with? We call this axis first split. Maybe this is it, and if let's draw those. So and if yes, this would on this side I want the power trainer at each classification. So let's see. So if we got a point here, so let me draw a new point. Let me pick a more interesting one. Let's see. So say we get a new point here, something like that. So this new point. So they say this is our x. So this is x. So we come down here. We say, okay, it's greater than 1. So the first split tells us to go down this path. So we go down here. Now, is xi2 greater than 1? And no, it's not, right? So we go down here. Now we're at this node, and we say, is xi1 greater than 2? And yes, it is. So we're down here, and we classify this according to the majority vote, which says make it a 0. So that would be classified as a 0, a new test point. And if we got a point here, we would do the majority vote again. So maybe this point here, we would say it's a 1, and so on. So you get the idea. So
Introducing Mixed and Key Studio Edition. The future of key detection.
You'll need to know how the decision tree classifier works before you can learn the working nature of the random forest algorithm. So how does it work? In random forest, we grow multiple trees as opposed to a single tree in cart model. To classify a new object based on attributes, each tree gives a classification, and we say the tree votes for that class. The forest chooses the classification having the most votes over all the other trees in the forest. And in the case of regression, it takes the average of the outputs by different trees. So let's look at the advantages of the random forest. So the same random forest algorithm or random forest classifier can be used for both classification and regression tasks. Random forest classifier will handle the missing values and maintain accuracy when a large proportion of the data are missing. When we have more trees in the forest, random classifiers won't overfit the model. It has the power to handle large datasets with higher dimensionality. If we look at the disadvantages of random forest, however, it surely does a good job at classification, but it's not as good as for regression problems, as it does not give precise continuous nature predictions. In the case of regression, it doesn't predict beyond the range of the training data, and they may overfit datasets that are particularly noisy. Random forest can feel like a black box approach for statistical modelers. You have very little control of what the model does. You can try different parameters and random seeds. So what are the applications of random forest? So let's check a few of them down below. So we can use them in the banking sector. So these are for finding loyal customers and finding the fraud customers. It can be used in medicine, where we identify the correct combination of components to validate medicine. Random forest algorithms are also helpful for identifying disease by analyzing the patient's medical records. In the stock market, random forest algorithm is used to identify the stock behavior as well as the expected loss or profit by purchasing a particular stock. In e-commerce, the random forest is used in a small segment of the recommendation engine for identifying the likelihood of a customer liking the recommended products, and this is based on similar kinds of customers. In computer vision, the random forest is used for image classification. Microsoft have used random forest for body part classification for Xbox Connect. And other applications involve lip reading as well as voice classification. Let's take a look at the random forest pseudocode and how it works. So it works in the following manner, where each tree is planted and grown as follows. So assume a number of cases in the training set is n. Then the sample of these n cases is taken at random, but with replacement. The sample will be the training set for growing the tree. If there are m input variables or features, a number of m smaller than m is specified such that each node m variables are selected at random out of the dm. The best split on these m input variables is used to split the node. The value of m is held constant while we grow the forest. Each tree is grown to the largest extent possible and there is no pruning. And then we predict the data by aggregating the predictions of the n trees, which means majority votes for classification and average for regression. So to perform the predictions using the trained random forest algorithm, we need to pass the test features through the rules of each randomly created trees. Suppose, let's say we formed 1,000 random decision trees to form the random forest. Say we're detecting if an image contains a hand. Each random forest will predict a different outcome or class for the same test feature. A small subset of the forest will look at a random set of features, for example a finger. Suppose 100 random decision trees predict some 3 unique targets, such as a finger, thumb, or maybe the male. Then the votes of a finger is tallied out of 100 random decisions, and likewise for the other 2 targets. If finger is getting highest votes, then the final random forest returns the finger as its predicted target. This concept of voting is known as majority voting, just like elections. The same applies to the rest of the fingers of the hand. If the algorithm predicts the rest of the fingers to be fingers, then the high-level decision tree can vote that the image is a hand. And this is why random forests are known as ensemble machine learning algorithm. Ensembles are a divide and conquer approach used to improve performance. The main principle behind ensemble methods is that a group of weak learners can come together to form a strong learner. Each classifier is individually a weak learner, while the classifiers taken together are a strong learner. And thus ensemble methods reduce the variance and improve performance. Before we end the lecture, let's take a look at some terms and definitions that you might come across, such as bagging and boosting. Bootstrap aggregating is also known as bagging, which is a machine learning ensemble meta algorithm designed to improve the stability and accuracy of the machine learning algorithms used in statistical classification and regression. It also reduces variance and helps to avoid overfitting. Boosting is a machine learning ensemble meta algorithm for primarily reducing bias and also variance in supervised learning, and a family of machine learning algorithms which also convert weak learners into strong ones. Algorithms that achieve hypothesis boosting quickly become simply known as boosting. Okay, so that is it. Thank you for watching. Please don't forget to like, subscribe and share. Click that bell icon to get notified of more fun and easy machine learning algorithms. Also, animating these videos takes a a lot of time and effort, so please don't forget to support us on Patreon. So in the following
In this video, we look at a different category of ensemble learners called as extra tree classifiers. Extra tree classifiers seem much more faster when compared to a random forest. So we'll try to bring out the differences between an extra tree classifier and a random forest. So let's get started. Before looking at what an extra tree classifier is, let's first look at how a random forest works. So let's consider a simple data set with m features and n rows. In a random forest, we grow multiple trees such that each tree comprises of the square root of the total number of features that are present. So in our case, we have m features. So each tree would have square root of m features to train on. Additionally, we'll be making use of bootstrap samples or samples with replacement. That is where we have the out of the bag error score that grow multiple trees such that each tree comprises of the square root of the total number of features that are present. So in our case, we have m features. So each tree would have square root of m features to train on. Additionally, we'll be making use of bootstrap samples or samples with replacement. That is where we have the out of the bag error score that we can use later on for validation. Now, how is an extra tree classifier different? The very first difference of an extra tree classifier lies in how we select samples. In extra tree classifier, we will be selecting samples for every decision tree without replacement. So all the samples would be unique in nature. The total number of features selected still remain the same. That is square root of the total number of features if you're using a classification task. So what exactly is the difference between an extra tree classifier and a random forest? The main difference between random forest and extra tree classifier lies in the fact that instead of computing the locally optimal split for a feature combination, a random value is selected for the split for the extra tree. So again, the whole idea is rather than not spending time in finding out the best splitting point, I randomly pick up a point and split based on that. This leads to more diversified trees and less splitters to evaluate when training an extremely random forest. When extra tree classifiers were tested with the readily available data sets, we observed that when we had noisy features in our data set, extra tree classifiers seem to outperform random forest. However, when all the features are relevant and when we train both extra tree classifier as well as a random forest, both methods seem to have achieved the same performance, be it in terms of accuracy, AUC ROC values or the F1 score that we are chasing. This was my attempt at explaining how an extra tree classifier is
Our planet never ceases to amaze us.
Machine sounds so complicated, but it's not so complicated. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to cover Adaboost and it's going to be clearly explained. Note, this StatQuest shows how to combine Adaboost with decision trees because that is the most common way to use Adaboost. So, if you're not familiar with decision trees, check out the quest. We will also mention random forests, so if you don't know about them, check out the quest. We'll start by using decision trees and random forests to explain the three concepts behind Adaboost. Then we'll get into the nitty-gritty details of how Adaboost creates a forest of trees from scratch and how it's used to make classifications. So let's start by using decision trees and random forests to explain the three main concepts behind Adaboost. In a random forest, each time you make a tree, you make a full-sized tree. Some trees might be bigger than others, but there's no predetermined maximum depth. In contrast, in a forest of trees made with Adaboost, the trees are usually just a node and two leaves. Oh no, it's the dreaded terminology alert. A tree with just one node and two leaves is called a stump. So this is really a forest of stumps rather than trees. Stumps are not great at making accurate classifications. For example, if we were using this data to determine if someone had heart disease or not, then a full-size decision tree would take advantage of all four variables that we measured, chest pain, blood circulation, blocked arteries, and weight, to make a decision. But a stump can only use one variable to make a decision. Thus, stumps are technically weak learners. However, that's the way Adaboost likes it, and it's one of the reasons why they are so commonly combined. Now back to the random forest. In a random forest, each tree has an equal vote on the final classification. This tree's vote is worth just as much as this tree's vote or this tree's vote. In contrast, in a forest of stumps made with Adaboost, some stumps get more say in the final classification than others. In this illustration, the larger stumps get more say in the final classification than the smaller stumps. Lastly, in a random forest, each decision tree is made independently of the others. In other words, it doesn't matter if this tree was made first or this one. In contrast, in a forest of stumps made with Adaboost, order is important. The errors that the first stump makes influence how the second stump is made, and the errors that the second stump makes influence how the third stump is made, etc., etc., etc. To review, the three ideas behind Adaboost are: 1. Adaboost combines a lot of weak learners to make classifications. The weak learners are almost always stumps. 2. Some stumps get more say in the classification than others. 3. Each stump is made by taking the previous stump's mistakes into account. Bam! Now let's dive into the nitty-gritty detail of how to create a forest of stumps using Adaboost. First, we'll start with some data. We create a forest of stumps with Adaboost to predict if a patient has heart. Note, the sample weight indicates chest pain and blocked artery status and their weight. The first thing we do is give each sample a weight that indicates how important it is to be correctly classified. Note, the sample weight is different from the patient weight, and I'll do the best I can to be clear about which of the two I'm talking about. At the start, all samples get the same weight. 1 divided by the total number of samples. In this case, that's 1 divided by 8. And that makes the samples all equally important. However, after we make the first stump, these weights will change in order to guide how the next stump is created. In other words, we'll talk more about the sample weights later. Now we need to make the first stump in the forest. This is done by finding the variable, chest pain, blocked arteries, or patient weight that does the best job classifying the samples. Note, because all of the weights are the same, we can ignore them right now. We start by seeing how well chest pain classifies the samples. Of the 5 samples with chest pain, 3 were correctly classified as having heart disease, and 2 were incorrectly classified. Of the 3 samples without chest pain, 2 were correctly classified as not having heart disease, and 1 was incorrectly classified. Now we do the same thing for blocked arteries and for patient weight. Note, we used the techniques described in the decision tree StatQuest to determine that 176 was the best weight to separate the patients. Now we calculate the Gini index for the 3 stumps. The Gini index for patient weight is the lowest. So this will be the first stump for patient weight is the lowest. So this will be the first stump in the forest. Now we need to determine how much say this stump will have in the final classification. Remember, some stumps get more say in the final classification than others. We determine how much say a stump has in the final classification based on how well it classified the samples. This stump made 1 error. This patient, who weighs less than 176, has heart disease, but the stump says they do not. The total error for a stump is the sum of the weights associated with the incorrectly classified samples. Thus, in this case, the total error is 1/8. Note, because all of the sample weights add up to 1, total error will always be between 0 for a perfect stump and 1 for a horrible stump. We use the total error to determine the amount of say this stump has in the final classification with the following formula. Amount of say equals 1/2 times the log of 1 minus the total error divided by the total error. We can draw a graph of the amount of say by plugging in a bunch of numbers between 0 and 1 for total error. The blue line tells us the amount of say for total error values between 0 and 1. When a stump does a good job and the total error is small, then the amount of say is a relatively large positive value. When a stump is no better at classification than flipping a coin, i.e., half the stumps are correctly classified and half are incorrectly classified, and the total error equals 0.5, then the amount of say will be 0. And when a stump does a terrible job and the total error is close to 1, in other words, if the stump consistently gives you the opposite classification, then the amount of say will be a large negative value. So if a stump votes for heart disease, the negative amount of say will turn that vote into not heart disease. Note, if total error is 1 or 0, then this equation will freak out. In practice, a small error term is added to prevent this from happening. With patient weight greater than 170, prevent this from happening. With small error, then this equation will freak out. In practice, a small error term is added to prevent this from happening. With patient weight greater than 176, the total error is 1/8, so we just plug and chug. And the amount of say that this stump has on the final classification is 0.97. Bam! Now that we've worked out how much say this stump gets when classifying a sample, let's work out how much say the chest pain stump would have if it had been the best stump. Note, we don't need to do this, but I think it helps illustrate the concepts we've covered so far. Chest pain made 3 errors, and the total error equals the sum of the weights for the incorrectly classified samples. So the total error for chest pain is 3/8. We can get a sense of what the amount of say will be by looking at the graph when total error equals 3/8. So we are expecting the amount of say to be between 0 and 0.5. Now we plug 3/8 into the formula for the amount of say and do the math. And the amount of say that the chest pain stump would have had on the final classification is 0.42. I'll leave the blocked artery stump as an exercise for the viewer. Now we know how the sample weights for the incorrectly classified samples are used to determine the amount of say each stump gets. Bam! Now we need to learn how to modify the weights so that the next stump will take the errors that the current stump made into account. Let's go back to the first stump that we made. When we created it, we did not emphasize the importance of correctly classifying any particular sample. But since this stump incorrectly classified this sample, we will emphasize the need for the next stump to correctly classify it by increasing its sample weight and decreasing all of the other sample weights. Let's start by increasing the sample weight for the incorrectly classified sample. This is the formula we will use to increase the sample weight for the sample that was incorrectly classified. We plug in the sample weight from the last stump, and we scale 1/8 with this term. To get a better understanding of how this part will scale the previous sample weight, let's draw a graph. The blue line is equal to E raised to the amount of say. When the amount of say is relatively large, i.e., the last stump did a good job classifying samples, then we will scale the previous sample weight with a large number. This means that the new sample weight will be much larger than the old one. And when the amount of say is relatively low, i.e., the last stump did not do a very good job classifying samples, then the previous sample weight is scaled by a relatively small number. This means that the new sample weight will only be a little larger than the old one. In this example, the amount of say was 0.97, and E raised to the 0.97 equals 2.64. That means the new sample weight is 0.33, which is more than the old one. Bam. Now we need to decrease the sample weights for all of the correctly classified samples. This is the formula we will use to decrease the sample weights. The big difference is the negative sign in front of amount of say. Just like before, we plug in the sample weight. And just like before, we can get a better understanding of how this will scale the sample weight by plotting a graph using different values for amount of the negative amount. Then we scale the sample weight by a value close to 0. If the sample weight by a value just a little small was 0.7, 0.0, we plug in 0.33 for the sample that was incorrectly classified. All of the other samples get 0.05. Now we need to normalize the new sample weights so that they will add up to 1. Right now, if you add up the new sample weights, you get 0.68. So we divide each new sample weight by 0.68 to get the normalized values. Now, when we add up the new sample weights, we get 1, plus or minus a little rounding error. Now we just transfer the normalized sample weights to the sample weights column, since those are what we will use weights to make the second stump in the forest. Bam! Weighted Gini indexes to determine which variable should split the next stump. The weighted Gini index would put more emphasis on correctly classifying this sample, the one that was misclassified by the last stump, since this sample has the largest sample weight. Index, we can make a new collection So we start by making a new but empty dataset that is the same size as the original. Then we pick a random number between 0 and 1. And we see where that number falls when you use the sample weights like a distribution. If the number is between 0 and 0.7, then we would put this sample into the new collection of samples. And if the number is between 0.7 and 0.14, and if the number is sample to 1 and samples. Imagine the first number I picked was 0.7. Then I pick another random number and get 0.42. New collection of samples. This sample into my new collection. We have added this particular sample to the new collection. Add samples to the new collection until the new collection is the same size as the original. Ultimately, this sample was added to the new collection of samples 4 times. Reflecting its larger sample weight. Now we get rid of the original samples and use the new collection of samples. Lastly, we give all of the samples equal sample weights, just like before. However, that doesn't mean the next stump will not emphasize the need to correctly classify these samples. Because these samples are all the same, they will be treated as a block, creating a large penalty for being misclassified. Now we go back to the beginning and try to find the stump that does the best job classifying. First tree makes influence how the second tree is made, and how the errors that the second tree makes influence how the third tree. Double bam! Now we need to talk about how a forest of stumps created by Adaboost makes classifications. Imagine that these stumps classified a patient as has heart disease, and these stumps classified the patient as does not have heart disease. These are the amounts of say for these stumps, and these are the amounts of say for these stumps. Now we add up the amounts of say for this group of stumps. The patient is classified as has heart disease because this is the larger sum. Triple bam! To review, the 3 ideas behind Adaboost are: 1. Adaboost combines a lot of weak learners to make classifications. The weak learners are almost always stumps. 2. Some stumps get more say in the classification than others. And 3. Each stump is made by taking the previous stump's mistakes into account. If we have a weighted Gini function, then we use it with the sample weights. Otherwise, we use the sample weights to make a new dataset that reflects those weights. Hooray! We've made it to the end of another exciting stat quest.